In stats, we talked a little more, little more about the t-distribution. The main thing you need to memorize is this statement right here. We use the t-distribution when you do not know what the population standard deviation is. Another way to approach it is you only have S, the sample standard deviation. So the reason is because S is more variable, it's not as accurate as sigma. Like, I wish we could have sigma because that would give us more precise statistics, but in the real world, it's not always available to us. So that's what I typed right above this, right there. When you're doing a real experiment, you typically don't know what sigma is. And all you have to work with is S, which just simply isn't as accurate as sigma. So this guy Gossett, he had to derive a new way of doing math, of approximating things. It's still based on a bell curve, it's just not the bell curve. So when you're looking at this, if you call this blue curve the Z curve, remember that is your perfect bell curve, not really my drawing, but if you're looking at the Z curve, it's perfection in terms of bell-shaped. T is more variable, it's more spread out, but yet it still is bell-shaped. So it looks something like that. And that's T. They're both centered around 0. They're both bell-shaped, but T is more variable. All right? The other thing that's a little bit confusing is there are infinite T curves, T distributions, whereas there is just one Z curve. So let's look at table B on the formula chart. I mean, it talks about it all right here. But let's jump to table B. And it really explains quite a bit, I think. So by the way, table A is Z. So you can look at the left column down there, right below table A, it says Z. When you get to table B, it says DF, and just to the right of table B, it says T distribution. And when we scroll through this thing, the top, we'll look at how to interpret that down the road. It's kind of weird at the top. Oh, I skipped over it. By the way, look, it's bell-shaped right here, whereas Z is also bell-shaped. So they're both very similar. They printed that picture for you, and chances are that'll be a question. Describe the T curve, and it's bell-shaped. It's symmetric. But all of these rows here are T curves. So like that is one T distribution. And here's another, here's another, here's another. And as N increases, it approaches the Z distribution. So back to our notes. This pen's not working. There it goes. Back to our notes. As the number of degrees of freedom increase, it is approaching the Z curve. So degrees of freedom is this thing that's defined in that bold statement at the very bottom. So you can compare degrees of freedom as like number of observations, subtract the number of parameters you're observing. So in this case, if we are, estimating. In this case, we're estimating the mean, one parameter, So I subtract 1 from my sample size, and that's my degrees of freedom. So whenever I move to the chart, all of these are degrees of freedom on the left, different sample sizes. And if I need a confidence level based on a sample size of, say, 22 at 95%, I'm looking at this number right here. Did I say 22? 22 would be this one. Because it's n minus 1. All right. So back to the examples on the handout, you need to know how to use the T-curve, or the table B, and it asks you how to read it. So you need your formula chart to look at this, and if you need to freeze the screen and go back and forth, we are looking for T. So look at the very bottom of table B, 95, and go up to the 12th row. So when you do that, you should get a T-score of 2.179. If you're confused how it's being calculated, that's the central area. So if we're looking at 95%, this is 0.25, so this is the 975 percentile. That means inverse T, area 975, DF is 12. And you get that. But I don't like to use inverse T. Just use your table B and it prints this right here. You don't have to know how to use inverse T. You can just use the table. So like for 20 degrees of freedom, go over to the 99th column, 0.99, and go up to the 20th row, and you should see the number 2845. For a large sample size, greater than 1,000, we're going to use the infinity row, which is the Z-curve. All right. If they ask for a weird sample size, because remember DF is n minus 1, so this would be a sample size of 33. Then we round down because we want to be conservative and not overstate what we sampled, just because that row is not available on the table. So I go down to the 30th and I see this printed for T. Same with that bottom one. I round down to 30. And use the same exact T-score. If that bothers you, the rounding, you could use the calculator and do inverse T, area is 975, degrees of freedom is 32, and when you do that, you get a different T-score, but it is barely different, 2.0369. All right. Likewise, if you have 36 degrees of freedom, you get a t-score very similar at 2.0281. But you don't have to do it this way. Just use the table. All right? It's just some people get bugged by that and they want it more precise. One other thing to note, you might write this larger than I can write here. This is for confidence intervals. For a mean. Not for hypothesis tests. Not for proportions. All right. All right, we moved forward and we tried to do a t-test. We didn't quite finish in third period. We'll finish the next day. But I bet we can finish it here. So let's say I'm doing a hypothesis test for a mean. Very similar steps to a 1-prop z-test. I'm going to define the true mean. I'm going to set up my hypotheses. It's going to be less than, greater than, or not equals. And I set my alpha. The plan step is a tiny bit different from the last hypothesis test we did. For a 1 proportion z-test, you do the large counts, and it has to be random. For a t-test, it's got to be random. And the sample size has to be large. That's the central limit theorem. If that's true, then you know it's approximately normal. One of the dumb things we do in stats, though, is we always bend the rules. Because in the end, we want to do stats, and if they take too small of a sample, so if n is smaller than 30, look at the graph. If symmetric with no outliers, then assume normal. All right? So one of the two scenarios will play out. Either we need a large sample and you just proceed, or if it's a small sample, you got to look at the graph and double check that it doesn't look alarming. For the do step, you can name the test or write the formula. You don't have to do both. List everything out. Write down X bar, write down S, write down DF, write down the p-value, compare the p-value to alpha, and then conclude. So you already know how to do a lot of this. The main thing I wanted to make sure I pointed out was this right here. That's a little different. The calculator takes care of the rest. So let's give a test a try. We have this healthy stream problem. You need to type all that data into a spreadsheet. So maybe hit pause and do that. I named mine A, and I have all 15 values. Okay? So back to the problem. We're going to do the full 4-step process. So the state step, I am estimating the true mean. Looks like they're looking at dissolved oxygen in a stream. Because they're concerned about aquatic life. The crucial number that we are worried about is 5. So if values are too low, we're going to be alarmed. We are worried about too small of a dew level. They tell us to let alpha be 0.05, and then we move on to the plan step. We have a random sample. They looked at random locations in the stream. N is less than 30. That's bad. But let's look at the graph. And the graph is probably going to be symmetric with no outliers. So the graph looks like this. Yeah, there's a little pileup right here off center, but I mean, that's just one value. There's not a huge gap, so we can say symmetric with no outliers. Another check, if you're really concerned, is look at plot type. You can compare it to the normal curve. And since all the dots fall really close to this line, the line resembles the bell curve, then you're safe to assume normal. So there's a couple reasons why we can proceed. All right? So I'm going to say, but graph looks symmetric with no outliers. Assume normal. So you move on to the do step, and we got to jump to the spreadsheet. We're going to ask the calculator to do a t-test for us. You can just write the name, or you can write this formula if you want. You don't have to write this. But let's do it on the calculator. You go to Menu, Stats, Stat Tests, and we want a t-test. It asks you, did they give us a bunch of stats like X bar and S, or did they give us a data set? And they gave us a data set. So you just click OK. This is my null, 5. I named it A. You leave that frequency list alone. Change HA to a less than. And first result, this is where they print it, so you can leave that alone. So you just change the null. You change the name of your list and HA. You say OK. And you copy all your stats down. All right? So we get, I wrote it down somewhere, X bar of 47713. S is 9396. Degrees of freedom was 14. N minus 1, 15 minus 1. T ends up being negative 9425. The p-value ends up being 1809, which is larger than alpha. So when we move to the conclude step, we are going to fail to reject. The evidence does not suggest. The true mean DO level in the stream is less than 5 milligrams per liter. There's another question at the bottom. We'll do it later. But there's your first t-test. I hope you thought it was easy. It should be easy. All right, bye.